All right, so if we continue with indeterminate forms, we're going to look at infinity minus infinity, okay? We're going to try to combine terms and get to 0 over 0 or infinity over infinity and then use L'Hopital's rule. This example, find its limit. Well, a lot of people like to think of the secant as 1 over cosine. So let's do a rewrite. Let's say this is the limit as x approaches pi over 2 from the left of 1 over the cosine minus the tangent. All right, let's see what kind of form I have right here, okay? As x goes to pi over 2, what does the cosine go to? Think about your unit circle. Your cosine up here is what? 0. So if the top stays fixed and the bottom goes to 0, this whole part right here goes to infinity, right? Minus, what does the tangent go to as x approaches pi over 2 for the left? The easiest way to think about this is think of your graph of your tangent function. Here is pi over 2, a what? Vertical asymptote. Your tangent function does something like that, right? As you approach pi over 2 from the left-hand side, pi over 2 from the left, your graph is going off to infinity. So you basically have the form infinity minus infinity. So what are we going to try to do? We're going to try to combine things. So we're going to try to do this subtraction right here. So let's do a rewrite. Limit as x approaches pi over 2 from the left of 1 over cosine of x minus sine of x over cosine of x. I'm going to call the tangent. And that way I get a common denominator. Well, this will give me the limit as x approaches pi over 2 for the left of, my numerator is just going to be 1 minus sine of x, and my denominator is going to be cosine of x. Now let's see what kind of situation I have going on. As x approaches pi over 2 for the left, what does my cosine approach? It approaches 0, right? As x approaches pi over 2 from the left, my sine approaches what? 1? What's 1 minus 1? 0. So I have indeterminate form 0 over 0. So what do we do for that? Well, I know what to do for that. I'm going to try to use L'Hopital's rule. So I'm going to say this is equal to, and I like to put this mark just to show that I'm using L'Hopital's rule here. It's equal to the limit as x approaches pi over 2 from the left again, pi over 2 from the left. Now take the derivative at the top, take the derivative at the bottom. What's the derivative at the top? Negative cosine of x. What's the derivative at the bottom? Negative sine of x. Well, what's a negative over a negative? A positive. So I can say this is the limit as x approaches pi over 2 from the left of cosine of x over sine of x. Now let's see if that helped me any. As x approaches pi over 2, my cosine approaches 0. As x approaches pi over 2, my sine approaches 1. So what does that whole value give you? 0. So what are we saying? If we have infinity minus infinity, we're going to try to combine it. Put it in a form where we get 0 over 0 or infinity over infinity and apply L'Hopital's rule. All right, for the next example, let's see. For the next example, let's look at this first of all. Earlier in the semester, we looked at e to the natural log of y. We could simplify, right? Remember if that exponent or the logarithm in the exponent has the same base as that, I could drop everything except the argument there. Now, this can be rewritten as y is equal to e to the natural log of y. Okay, that's a property of logarithms. Keep that in the back of your head, okay? We're about to use it in a little bit. All right, so next what we're going to look at is we're going to look at another indeterminate form or some more indeterminate forms. Here we're going to have 0 to the 0, infinity to the 0, and 1 to the infinity. Okay, we're going to group all those together. Now, what are we going to do with these? We're going to introduce an independent variable, and we're going to take the log of both sides and so forth. And it's actually easier to show you than it is to explain it. All right, so let's look at this. Suppose we have this example. In part A, we're going to want the limit as x approaches 0 from the right of x to the x. All right, let's see which form we have. As x goes to 0, that goes to 0, and that goes to 0, so I have the form 0 to the 0. So I have that form, right? So what do I do if I have that form? Well, what I do is I say, let y equal to whatever I'm taking the limit of. In this case, x to the x. All right. Then what we do is we take the natural log of both sides. Natural log of y is equal to the natural log of x to the x. Then we can say the natural log of y is equal to x times the natural log of x. So what did I do? I just used that property of logarithms where I brought that exponent of argument out to the front. So what I'm going to do, instead of taking this direct limit here, I'm going to take the limit of natural log of y first. So I'm going to sidestep over here. I'm going to say, okay, let's take the limit as x approaches 0 from the right, as x approaches 0 from the right, of the natural log of y. Let's take that limit. Well, I could do a rewrite. I could say this is the same thing as the limit as x approaches 0 from the right. The natural log of y is the same thing as x, natural log of x. X times natural log of x, right? Now, what do I have going on here? As x goes to 0, this part goes to 0, right? Times, what does the natural log of x go to as x goes to 0 from the right? Think about your natural log graph again, okay? Didn't we say it looked like that right there? And we had a vertical asymptote. So x approaches 0 from the right. Where's that natural log function going to? Negative infinity, right? And what did we learn in the last video about indeterminate form 0 times infinity? Rewrite this as a fraction. So let's rewrite that as a fraction. So this will be the limit as x approaches 0 from the right of natural log of x over 1 over x is the easiest way to write that as a fraction. As x approaches 0 from the right, what does the natural log do? It goes to negative infinity, we said, right? What does this bottom part go to? That'll go to infinity, right? Infinity over infinity, I like that. I could use L'Hopital's rule. So I can say, all right, I'm going to use L'Hopital's rule. Limit as x approaches 0 from the right of, take your derivative of your numerator. That's just 1 over x, right? Your derivative of your denominator is negative 1 over x squared. All right, let's try to simplify this. This is the limit as x approaches 0 from the right of 1 over x times the reciprocal of this one, so times negative x squared over 1. This x divides out with one of those x's, and we get the limit as x approaches 0 from the right of negative x. So what does that give me? That gives me negative 0, or just what? 0. All right, so what did we just say here? What did we just conclude? We just concluded that the limit as x approaches 0 of natural log of y is equal to what? 0. So we just concluded the limit as x approaches 0 from the right of the natural log of y is equal to 0. That's still not exactly what I want. I want the limit of this thing, right? But that helps me. Let's go back to this. Let's go back to that. The limit as x approaches 0 from the right of x to the x. X to the x. Well, I can say that's the limit as x approaches 0 from the right of, we call x to the x what? Y. So I can replace this x to the x with y from that. All right, well that doesn't help me any. Well, kind of does. Limit as x approaches 0 from the right. What we say is another way to write y. We could write it as e to the natural log of y. So instead of y, I'm going to call that e to the natural log of y. Make sure that makes sense to you. As long as this function right here is continuous, which e is continuous, I can bring this limit up to the exponent and rewrite this as e to the limit as x approaches 0 from the right of natural log of y. Well, that's e to the what? What's the limit as x approaches 0 natural log of y? That was what? 0. So I can replace all that with 0. What's e to the 0? 1. So this limit is 1. How did I do it again? I let y equal to what I was trying to find the limit of. Took the natural log of each side, used a property, then took the limit of this, and then used that to help me. All right, let's do another one of these. We'll go ahead and call this one B. B. Part B. Part B, we're going to look at, it looks like evaluate this limit. Limit as x approaches 0 from the right of 1 plus the sine of 4x all to the cotangent of x. I'm going to make sure I'm on the screen because I'm at the very top. No. I'm going to rewrite this part. This was 1 plus sine of 4x all to the cotangent of x. Let's see if I'm on the screen now. Yeah, sure am. All right, let's figure out what we got going on here, okay? 1 plus the sine of 4x. If x approaches 0, that's like the sine of 0, right? Sine of 0 is 0. So 1 plus 0 is 1 inside the parentheses, right? Come down a little bit. So 1 inside the parentheses. How about the cotangent of x? As x approaches 0, what is the cotangent approach? Think about your graph of your cotangent that you had to graph at 110, math 110. Didn't it look like this? Had vertical asymptote at x is equal to 0 and x is equal to pi. And this thing did something like that. So as I approach 0 from the right, as I'm approaching 0 from the right, where's my graph going up to? Infinity. So that part goes to infinity. So I have indeterminate form 1 to the infinity. So what do? According to the statement we had on the board, what I do at this point is I let y equal to what I'm trying to take the limit of. 1 plus sine of 4x to the cotangent of x. Then I take the natural log of both sides. Natural log of y is equal to the natural log of 1 plus the sine of 4x to the cotangent of x. Then I can move this cotangent to the front of the natural log. So natural log of y is equal to the cotangent of x times the natural log of 1 plus sine of 4x. Now what I'm going to do is I'm going to come off to the side and say, all right, I do not know how to find this limit. So what I'm going to do is find the limit of the natural log of y. So I'm going to write limit as x approaches 0 from the right of natural log of y. I'm going to consider that, okay? But the natural log of y is also called this stuff, right? So I could take this natural log of y and replace it with all that stuff. So this is the limit as x approaches 0 from the right of cotangent of x times the natural log of 1 plus the sine of 4x. Well, I don't know about y'all, but I like to think of this as 1 over tangent. And if this is 1 over tangent times this stuff, I could say limit as x approaches 0 from the right of natural log of 1 plus the sine of 4x over the tangent of x. Let me figure out what I got going on now. As x approaches 0 from the right, what is my tangent function approach? So x approaches 0 from the right. Think about your tangent function. Looks like this, right? As I approach 0 from the right, the tangent function's approaching what? 0. So the bottom part is going towards 0. How about the top? As x approaches 0, I basically have the sine of 0. Sine of 0 is what? 0 plus 1 is 1. What's the natural log of 1? Natural log of 1 is 0. So I have indeterminate form 0 over 0. So let's try L'Hopital's rule. According to L'Hopital's rule, I'm going to rewrite this as the limit as x approaches 0 from the right of the derivative of the top part. How do you take the derivative of natural log? 1 over the argument. 1 over the argument times the derivative of the argument. Now, how do I take the derivative of the argument? Remember, that's what? Inside and outside, so I have to use the chain rule. Outside is sine, inside is 4x. Derivative of the outside is cosine at the inside times the derivative of the inside is what? 4. Get this out the way, it's getting kind of cluttered. How about the derivative of tangent? What is that? Secant squared? All right, let's try to make this look a little better, okay? So this is the limit as x approaches 0 from the right. This part I can put up top, and I could call that 4 times cosine of 4x over 1 plus sine of 4x. Oh, now isn't this part really over 1, over an understood 1? So I can multiply by the reciprocal now and say that's 1 over secant squared. So that gives me the limit as x approaches 0 from the right of 4 cosine of 4x over 1 plus sine of 4x times, what's the reciprocal of secant? Cosine, right? Let's try to evaluate this limit, see what we get. So I'm going to have 4 times, what's the cosine go to? Well, if x goes to 0, the cosine goes to 1, right? Over here, I have the 1 I'm going to bring down, plus, as x goes to 0, the sine function goes to 0. And as x goes to 0 here, the cosine function goes to what? 1? Then we have to square that, right? Well, what does that give me if I clean all that up? I get what? Just 4, right? Just 4. Let me come down a little further with this. Let me call this 4. Let me sure I'm still in the shot. Yeah. So if that's 4 then, what did I just conclude? I just concluded this limit is equal to 4. So I just concluded the limit as x approaches 0 from the right of the natural log of y is equal to 4, we said. I'm about to use that in a second. All right, but what I really want is this limit here. So we go back to that limit. The limit as x approaches 0 from the right of 1 plus the sine of 4x to the cotangent of x. I could do a rewrite. I could say this is the limit as x approaches 0 from the right. What is all this stuff? We said let's let all that stuff equal to what? Y. So I could call all this stuff y. And this is the limit as x approaches 0 from the right. But y, a more creative way to write it is e to the natural log of y, right? So I could say e is continuous, so I could pull the limit up to the top here and say this is e raised to the limit as x approaches 0 from the right of natural log of y. So that's e. And what is that limit right there? That limit we just said was what? 4? So I can replace all this part with 4. And my limit is e to the 4th. Remember, this stuff is hard. You have to try this stuff over and over and work these problems, not just watching me work them. So make sure you can do them yourself.